Hello, this is Huayu Li. I'm a PhD student at the University of Michigan Ann Arbor. I'm co-advised by Professor Ilya Komnovsky and Professor Anouk Gerard. The title of our paper is Set-Theoretic Failure Mode Reconfiguration for Stuck Actuators. Maintaining the safe operation of system is critical for applications such as spacecraft, aircraft, and autonomous vehicles. On September 8, 1994, US Air Flight 427 crashed when it's approaching the runway for landing, killing all 132 people on board. The investigation concludes that the accident is caused by a jammed rudder. On July 29, 2021, a spacecraft module docked to the International Space Station accidentally fired its thruster continuously, causing the space station to tilt about 45 degrees and lost attitude control for more than an hour. The officials claimed that the crew and the space station were never in any danger. Yet a similar incident occurred for the second time in less than 3 months on October 15. For autonomous driving, automotive companies are developing systems with redundancy, such as dual steering motors and redundant brake actuators, to avoid car accidents caused by component failures. Motivated by these facts, our study focused on the systematic design of failure mode and effect management, FMEM, for systems with redundant actuators that can get jammed. These systems often operate in constrained environment while trying to check reference commands, and it's required that they can operate without constraint violation at any time, even when failures occur. So our design goals include that in case of a single point of failure, the operation can be reconfigured, and then in the new mode, another single point of failure cannot lead to safety hazards. Meanwhile, the system availability should be maximized throughout the operation. More specifically, the problem is to handle stuck actuators and the sequential failures to ensure the safe operation at any time while performing reference checking. We assume that only one failure can happen at a time, and there's instantaneous detection and isolation of the failure, as well as a large time between subsequent failures. The number of the working actuators should be greater than the number of the reference. There's much literature on fault-tolerant control and reconfigurability analysis. Some related studies are shown in this page, but we found that a systematic approach that can achieve all of our goals is still missing. In our previous work focusing on failed actuators being set to the zero position, we proposed a method that exploits nesting between constrained admissible and recoverable sets designed offline to guarantee the existence of a recovery sequence. And the reference governor is applied online to check reference commands while imposing constraint satisfaction using the remaining working actuators. So in this work, we extend this method and reformulate our design to address a much more general case when actuators can get stuck. Here's an outline for the rest of the presentation. I'll first introduce the mode-dependent dynamics and constraints of the type of system that we're considering, and then we'll formally define the constraint admissible and recoverable sets, which are then used to develop the FMEM strategy. And finally, we'll see a numerical example using the proposed method. We consider systems with N actuators. M denotes the mode, and LM labels the working and failed actuators using zeros and ones. An example of all possible failure scenarios for N equal to 2 is shown on right. The number in the boxes label the working actuators. This diagram on top shows an overview of the system dynamics. We first define 3 types of input representations, where U is the open loop input, mu is the vector of the working inputs, and D is the vector of the failed inputs. Then for systems represented by the open loop dynamics in equation 1 and 2, a stabilizing controller is designed to command the working input mu, where Km is the feedback gain, and Gm and Hm are the feedforward gains. Equation 3 represents the closed-loop system dynamics. The sets of pointwise interim state and control constraints are given in equation 4 by a set of inequalities. Modifications to these constraints are considered to facilitate the subsequent design of our FMEM approach. The tightened and relaxed constraints are defined by equation 5 and 6. Here's the framework for the safe operation and reconfiguration to be implemented online. During the operation in each mode, the system runs the upper part of the loop and performs reference checking using the reference governor. Once failure is detected and isolated, a recovery sequence will be generated, and the system will run with the sequence until the reconfiguration is finished. Before further discussion of the strategy, we first need to define the constraint admissible and recoverable sets. The constraint admissible set is a set of constant closed-loop input UM and initial states X0, such that constraints are satisfied for all future time. Note that the reference command is included in UM by definition. The constraint admissible set defined in the form of equation 7 has two nice properties. It's finally determined as given by equation A, and it's also invariant. The recoverable set is a set of initial states X0, such that there exists a recovery sequence V0 to V and M to steer the states into the state projection of O infinity M within a certain number of steps Nm. Meanwhile, the safety constraints XRM should be satisfied during the recovery. Now, during the safe operation online, a reference governor is applied, where the reference command is given by RK, while the modified command VK is updated at every time step by solving the optimization problem at the bottom. Once a failure is detected and isolated, a recovery sequence will be generated by solving the quadratic programming problem shown on the upper right. The safe reconfiguration condition is given by equation 10 and 11, which is to be designed offline to guarantee the existence of the recovery sequence. Equation 10 says that for all failure modes, except for the last one, we need all projections of the constraint admissible set of the preceding mode M prime to be the subset of the intersection of the recoverable sets of mode M. For equation 11, it says that for the last failure mode, mode omega, we need all constraint admissible sets of the preceding mode M prime to be subsets of the constraint admissible set of mode omega. Three mechanisms can be used to satisfy these conditions. We could tighten the constraints of the preceding mode, relax constraints of the successor mode during the reconfiguration, and allow more steps for the reconfiguration. Finally, let's apply our methods to a numerical example considering the longitudinal flight control of a Boeing 747. The dynamics constraint and mode definitions are showing on the left. The aircraft is trying to check a given climb rate trajectory, while the thrust and elevator is subject to failures by getting stuck. The offline design begins from mode 3, where both actuators have failed, and ends with the normal mode, mode 0. The three mechanisms to tighten or relax constraints are used to satisfy the reconfiguration conditions. The simulation results show that there's no constraint violation at any time during the operation and reconfiguration, and the climb rate follows as closely as possible to the reference command. We hope this presentation can give you a quick overview of our set theoretic approach to failure mode and effect management for jam or stuck actuators. For more details of the strategy, please refer to our paper. For future work, we plan to replace the instantaneous failure detection and isolation assumption with a failure detection and isolation and fault-tolerant control integrated approach to create a more systematic strategy. Thank you very much, and I'll be happy to take your questions.